What if I told you that black holes might be the universe's most sophisticated data storage system? That every star, every planet, every particle that falls into a black hole might not be destroyed, but rather archived in the most fundamental way possible. Today, we're diving into one of the deepest mysteries in modern physics, the black hole information paradox. So let's start with the basics. When something falls into a black hole, it crosses the event horizon, that point of no return where not even light can escape. For decades, physicists believed that whatever went in was simply gone, erased from existence. The information about that object's quantum state, its history, its very identity, all lost forever. But here's the problem. This violates one of the most fundamental principles in quantum mechanics. The principle of information conservation states that information in the universe cannot be destroyed. It can be scrambled, hidden, transformed, but never truly lost. So which is it? Do black holes destroy information, breaking the laws of quantum mechanics? Or do they preserve it somehow? This is what Stephen Hawking grappled with for much of his career. In the 1970s, Hawking discovered something remarkable: black holes aren't completely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This means black holes slowly evaporate over time. But here's where it gets really interesting. Hawking initially argued that this radiation was completely random, carrying no information about what fell into the black hole. If that were true, when a black hole finally evaporates completely, all the information about everything it ever consumed would vanish with it. This became known as the information paradox, and it created a crisis in theoretical physics. So how might information actually be preserved? There are several fascinating theories. First, there's the holographic principle. This suggests that all the information about what falls into a black hole isn't lost inside at all. It's encoded on the event horizon itself like a two-dimensional hologram that contains three-dimensional information. Imagine the event horizon as the ultimate hard drive, with every bit of data about the black hole's contents written on its surface in Planck-scale pixels. Then there's the idea of black hole complementarity. This theory proposes that information exists in two places simultaneously to an outside observer. Information is encoded on the event horizon, but to someone falling in, that same information passes through and exists inside the black hole. It's the same information, just described from different perspectives. More recently, physicists have proposed that information might escape through subtle correlations in Hawking radiation. The radiation isn't truly random. It's entangled with the black hole's interior in incredibly complex ways. As the black hole evaporates, it gradually releases information back into the universe, just scrambled beyond recognition. And Stephen Hawking himself eventually changed his mind. In 2004, he conceded a famous bet, acknowledging that information probably isn't destroyed after all. He proposed that quantum fluctuations at the event horizon might allow information to escape, encoded in the Hawking radiation in ways we're still trying to understand. Recent breakthroughs in quantum gravity and string theory have strengthened this view. The Page curve, a mathematical description of how information escapes from evaporating black holes, has been successfully calculated using cutting-edge theories, suggesting that information does indeed find a way out. But here's what makes this truly mind-bending. If black holes do preserve information, they're doing so in the most extreme conditions imaginable. We're talking about information encoded at the Planck scale, the smallest possible scale in physics, in a region where space and time themselves might break down into something we don't yet understand. Think about it. When a star collapses into a black hole, its entire history, every nuclear reaction, every photon it emitted, every gravitational interaction, might be preserved in quantum form. Not in any way we could easily read or retrieve, but fundamentally encoded in the structure of space-time itself. So are black holes cosmic data repositories? The answer appears to be yes, but not in any conventional sense. They're not hard drives you could plug into and download data from. They're more like the universe's most secure encryption system, where information is preserved but transformed into a form that's nearly impossible to decode. The information from that fallen star isn't lost. It's there, written in the quantum fabric of the event horizon, slowly leaking back out through Hawking radiation as the black hole evaporates over trillions upon trillions of years. The paradox isn't fully solved yet. We're still missing a complete theory of quantum gravity that would explain exactly how this preservation and retrieval works. But the consensus among physicists is clear: the universe doesn't delete files. It just has a really complicated filing system. And that, to me, is one of the most beautiful ideas in all of physics. Even in the most destructive, extreme environments in the cosmos, places where stars are crushed to singularities and space-time itself is torn apart, the universe still obeys its fundamental rule: information